Okay, so just a few quick announcements, intro stuff. We're still finishing up exam 3 grading. It was a bit tougher to get everything organized. We can't all sit in a room and just do it. But it should be done today. Almost all the grades are in for all the problems. So far everything looks pretty good, so don't worry too much. But we should hopefully have that to you by the end of the day. Then for homeworks, so we still have that ongoing. Of course, the homework that's due tomorrow is homework 12. It's a little different, right? It's not a problem set. We just want you to, spend a little bit of time, think up an idea for this process of science paper to make sure you're getting started and have an idea going. Regular problem set, there will be one for next week, which should be available tomorrow. But yeah, we're almost getting down to the end of the class. We got 2 more full weeks to go, and then there's this week and next week, and then there is one day after that where we'll probably do a review thing before the end of the semester. Oh, and the other thing about the exam I wanted to mention, so please, once you have your grades, double check that everything looks okay and that everything was submitted properly. I think if there was looks like there was any issue with your submissions or anything, we tried to contact everyone, but double check for us as well, right? We want to make sure you're getting the proper thing. Okay, so why don't we go ahead then and go on to physics stuff. So for the last 2 weeks, what we decided to focus on is this stuff about rotation. So we're not going to get quite to as much stuff as, there's a couple topics we would usually do, like either oscillations and waves a bit at the end that we probably won't get to, or I don't think we'll get to this semester with all the craziness. So, but we're going to get almost everything we would normally do. And I think this is the most important things that were remaining. So about rotation, the plan is basically to do what we did in the last section of the course as well for rotation. So, we introduced the idea of rotational coordinates, angular velocity, torque, angular acceleration a little bit earlier on as we went, just to try to say, oh yeah, you can also think about, angular motion instead of, or rotation instead of linear motion. But now we want to talk about the energy and the momentum that's involved in those systems, right? And so particularly today, we're going to focus on the energy. So I had a couple just things that in some sense should be review, but I know, people might it might not be fresh in your mind. And again, so the idea was we don't want to think of rotation as lots of little linear motions, right? That's difficult. You're constantly changing which way you're going and which way your forces are acting. So we instead define these rotating coordinates and sort of turn a 2-dimensional problem into a 1-dimensional problem. Right, and in particular, we're going to see a lot today this symbol omega, right, for the angular velocity, which is how fast your angle is changing. And so when you have like an object, like a circle, like a disk that we'll be talking about a lot today, doing a rotational motion with, remember, while the whole disk has the 1 omega, right, different pieces of the disk will have different velocities. The farther you get away from the center, the faster you have to go around the circle. Right? And then, of course, I could draw other parts of this circle, and they'd be going in completely different directions. Right? They wouldn't even be going at the same angle. Right? And so we've learned, again, about energy. And so we're going to talk about energy and momentum on Thursday and a bit more about torque next week. But in particular, what we want to focus on today is the fact that, this thing is moving around in a circle, right? Which means it has motion. Right? And we learned that the kinetic energy doesn't care about what direction something is going. Right? So the fact that part of the circle is moving left and part of the circle is moving right on the other side shouldn't matter for energy. Right? So since it's moving, there should be kinetic energy, and that's going to be our main focus. And the other thing we're going to talk a lot about today is a concept that was introduced briefly before, which was moment of inertia, which is the fact that some things are going to be harder to turn than other things. Okay, so about the kinetic energy. First, we can think about it just for a little point. So a point mass, no shape, If it's going around a circle, we already know how to figure out what its kinetic energy is, right? We know that it's moving with some velocity, right? So it has a kinetic energy that's 1/2 mv squared. Now, this velocity that's at that point is related to how fast its angular velocity is going and how far away from the center it is. Right? So v in this case was omega times r. And so you can just put that in and rearrange a bit. And you get that instead of 1/2 mv squared, you get 1/2 something, some expression times omega squared. Right? And that expression is mr squared. And that's the moment of inertia for this piece. Okay, I'm going to go ahead and go through the pre-lecture questions really quick. They were all about this idea of moment of inertia and rotational kinetic energy. People who answered them did pretty well, got majority were correct. So this one, you're going around in a circle on a merry-go-round, right? And if you go towards the center, does the moment of inertia increase or decrease or stay the same? Right, most got it right that it's correct that it's decrease, right? Because it goes down when the radius gets smaller. So the closer you get to the center, the easier it is to go around in a circle, right? And that means the moment of inertia decreases. Similarly, if you have a rod and you're like playing around with it, and unfortunately online it doesn't work as well that I don't have a good rod to play with, but it's easier to spin it around its center, right? Because more of the mass is close to the center than if you do it around its end and the mass is far away, especially if the other tip is very far away. And so again, the moment of inertia is bigger when you're spinning it around the end. And then most people got right that it's false, that an object that's spinning in place has no kinetic energy. Because while you might not write down a 1/2 mv squared for it because the whole thing is moving, you still need to take into account the fact that it's spinning, and that really means all the pieces of it are still moving around with some velocity. And that's really what you have to do when you're doing the moment of inertia, the rotational kinetic energy, is you have to think about all the different pieces, right? So again, there's a rotational kinetic energy. It's 1/2 this moment of inertia, omega squared. And that's just mr squared for the point mass going around a circle, right? But if it's an object, an extended object, it will be something, some number times mr squared of some kind, something like this, where r is just some length that's associated with the object, right? Right? And to do that calculation, right, you do fundamentally have to go and do an integral. Right? Because essentially what you do when you're finding these moment of inertias is you're saying, oh, it's mr squared for one little piece, right? And you have to say, okay, well, if I break up my object into lots and lots and lots of little pieces and figure out what all their mr squareds are, right? And then I integrate up, because integrals are addition, right? If you break something into pieces and add them up, that's doing an integral, right? And so you break it up into pieces, figure out the moment of inertia for each piece, add them back together, you do the integral. Now, we're not going to focus on actually doing those integrals in this class. You should just be aware that that's where it's coming from, right? And because you also get the same answer, essentially, for the integral, for the same shape every single time. Right? So when you do a disk, if you break it up into pieces and you do the integral and you get the moment of inertia, you're always going to get that it's 1/2 mr squared. You can change the mass, you can change the radius, right? But you always get 1/2 mr squared. Right? And so this number that goes out front is what you get from doing the integral, basically. And for us, we're just going to not want to redo it. We're just going to say, okay, I know for a disk, that's what it is. So you just find what this I is for various shapes around their center of mass. And for center of mass, again, we're not going to get too deep into this. You can really just think about it as the center of the object, if the object is uniform, and we're going to try to give you uniform objects. So you have your disk, and you get 1/2 mr squared from doing the integral. If you had a ring instead, you'd get 1/2 mr1 squared plus r2 squared, where r1 and r2 are the radiuses of the inside and the outside. If you have a square, you get 1/6 ma squared, where a is the side of the square. Right? And these all just come from doing an integral. And for us, we're basically just going to look at charts, right? So you need to be able to identify the shape you're looking at, and we're not expecting you to memorize all these 1/2s and quarters and thirds and twelfths, but just to be able to identify the shape which direction in 3 dimensions is the axis going through. Because like, for instance, in the cylinder, it matters if you're going along the cylinder or half, cutting it in half. Right, and then you go and you look up what the I is, the moment of inertia is for those shapes. Okay. So this is the chart from the textbook that I just broke up. There's similar ones from other books and other sources. Now, the other thing we might want to do for some problems is move where something is rotating. So maybe instead of rotating around the middle, you rotate it around the edge. And so when you do this, it's a relatively simple formula that you need to do, and it's called the parallel axis theorem, which I think sounds more intimidating than it really is. The idea is that once you know the I around that center of mass, that's on the chart, you look it up for the right shape. It's easy to find the moment of inertia for around any parallel axis. So if you move the rotation axis, or the axle, if you like to think of it like that, if you move it away from the center, like to the edge, for instance, you have to change the moment of inertia, and you have to just change it by adding a piece. So you take the same I from the chart, and you add a piece that looks like m times the distance you moved squared. Okay. And so this allows you to do more complex shapes with composite objects, but we're not going to spend a lot of time on that. So we might just have some object where you know it at the center, and then you have to move the axis a bit. Okay, so that's the sort of going through what we're going to need to solve the problems in terms of the energy. So for the rest of today, we're going to mostly just explore this through doing some examples, and then actually we have a video we want to play around with different moments of inertia. So again, I think probably if we cut here, it's the right time.